So let us understand what is the effect of strain rate on a strength and ductility. So these are the engineering stress strain diagram of three different strain rate. The first of all, strain rate is defined as d sigma upon del t, where del epsilon upon del t, epsilon is the engineering strain divided by time. So strain rate is d epsilon upon del t. It is inversely proportional to the time. So we can see that there are three curves, 1, 2 and 3. So red one is a higher strain rate, 2 is the medium, 3 is the lower strain rate. So if you increase the strain rate, the strength of the material is increasing, okay, and ductility of the material is decreasing. So lower strain rate material having the higher ductility as compared to the higher strain rate material. So let us understand why, if we increasing the strain rate, the strength is increasing. So let us consider a particular strain. Suppose that this is the fixed strain value of all the three materials. Okay, let us mark this point. So at this particular point, curve 1 has a higher strength. So because it has a higher strain rate, so in a higher strain rate, time is inversely proportional. So the time is fixed. Suppose that at this strain, higher strain rate material by very less time. So within that time, the dislocation generation is very high. Dislocation generation is very high. So this dislocation generation is interact to each other because at a higher strain rate time is very limited. Okay, so these dislocation generation interact to each other and form a dislocation barrier. Okay, so less time, it doesn't allow the dislocation to move, it interact to each other and form a dislocation barrier. That's why it has higher strain. So dislocation barrier is the main mechanism for increasing the strain. If the dislocation barrier is high, dislocation movement is restricted, that's why ductility also decreases. At the same time, at the lower strain rate, and suppose that epsilon 3, it has a higher time, okay, material get the higher time because lower strain rate time is higher, so this has a take a higher time to deform. So in this case, dislocation generations in a material interact to each other, but it does not form a strong barrier as compared to a higher strain rate. So it has few dislocation move if you apply the load, and few dislocation form a very weaker barrier, dislocation barrier. That's why the strength of material of lower strain rate is decreasing as compared to the higher strain rate. But it is not necessary that ductility only depend on the strain rate. The ductility is function of strain rate, temperature, okay, and gauge length, material, type of material, and gauge length. These are the factors which can control the ductility. Suppose that higher strain rate, lower the ductility, higher temperature, higher the ductility. Materials, what types of material you have, what are the chemical composition you have. Also the gauge length also play an important role. Higher the gauge length, lower the ductility, because higher the gauge length has a higher number of defects as compared to a smaller gauge